In this tutorial, we will be discussing intermolecular forces. Notice the difference in the word intermolecular and intramolecular. Intramolecular is the force between the atoms. These are the bonds, while the intermolecular are the attractions between the molecules. So the intra is within the molecule, while the inter is between the molecules. With the intramolecule, you only need one molecule to see that interaction, whereas with the intermolecular, you need multiple molecules. So let's do a compare and contrast of the intra versus inter forces. The intra is the attractive forces that hold the atoms together to form a bond, whereas the intermolecular are the attractive forces between the molecules and or the ions. Intra is the one that we've been working with before. The ionic bonds, the metallic bonds, the covalent bonds, whether they're true covalent or polar covalent. Whereas inter are the new ones that we're going to be discussing today. The interactions between these. The ion-ion interaction, ion-dipole, dipole-dipole such as hydrogen bonding, dipole-induced or induced-induced. When comparing one-on-one, the intermolecular forces are actually weaker in strength than the intramolecular. What makes intermolecular bonds appear stronger than the intramolecular is the quantity. The more intermolecular interactions there are, the stronger it is. And it's done by networking, kind of like a spider web. One strand of the spider web is really weak, but once you get several of them together to make a web, then it gets stronger. The size of the charge and the distance between the charges play a role in the intermolecular attractive strength. The larger the charge, the stronger the attraction. Also, the shorter the distance, the greater the attraction. So as these become closer together, they're going to be more attractive. Particles are attracted to each other by electrostatic attractive forces. This is referring to the positive and the negative type of interaction. The strength of the attractive forces vary. Some are small and some are large. It depends upon the types of the particles, whether it's a molecule or an ion, the size of the ion, and the polarity strength. The stronger the attractive forces between the particles, the more they resist moving or breaking apart. No material completely lacks the particle motion. However, it would take more and more strength to pull them apart the stronger it is. Here's a list of types of the intermolecular forces. Dispersion, also called the van der Waals forces, are for two things that are nonpolar. And we're going to discuss all of these in greater detail in a moment. Dipole-dipole are for polar molecules. All molecules have van der Waals, whether nonpolar, polar, or ionic. They all have van der Waals. However, the dipole-dipole is only for polar. Nonpolar doesn't really interact with the dipole-dipole. Hydrogen bonding is a special kind of dipole moment where the hydrogen has to be bonded to fluorine, oxygen, or nitrogen, and then that hydrogen here is then attracted to another molecule. This here is an oxygen. This is a water molecule where these are hydrogens up here. And this hydrogen is getting attracted to this oxygen over here. The ion dipole is if you have an ion here, let's say this is sodium inside, and then all these oxygens around it are attracted to it because they're partially negative. So once again, it's the positive to negative interactions with all of these The partially negative to the partially positive to the partially negative. Let's talk about dispersion forces first. Everything has dispersion forces. It's the formation of an induced dipole between two nonpolar molecules. The interaction or the contact causes an instantaneous dipole to form. This is associated with molecules having covalent bonding, such as organic or nonmetal compounds. Now, I mentioned before that all molecules and atoms have dispersion forces. However, because these are so weak, they're the weakest of all the intermolecular forces, unless it's a nonpolar molecule, it becomes kind of clouded by the other ones that are around it that had stronger intermolecular forces, such as hydrogen bonding or ionic bonding. And it has to do with the polarizability of the nonpolar molecule as a factor of strength. For instance, the bigger the molecule is, the easier the electrons are to move around, and so therefore they're going to interact more. It has to do with the size of the molecule, or the molecular mass. They're called dispersion forces or van der Waals forces. Notice when they're far away, there's no dipole moment. It's only when they get really close to each other that they're forced to interact. And this is why butter melts, but does not form necessarily a gas. And this is also why gases can liquefy, because if we push them together far enough, then they're forced to interact. So let's talk about the fact that the size matters. The dispersion forces are the weakest of all the intermolecular forces. The more contact spots, or the surface area, the greater the effect of the dispersion forces have on the molecule's physical properties, such as boiling point. For instance, these are both two different versions of pentane. You might not know what pentane is at this point, but it's C5H12. Both molecules have the same number of atoms. They both have 5 carbons. And they both have 12 hydrogens. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 3, 6, 9, 12. So they both have C5H12. But notice that they look dramatically different, because this one up here on the left-hand side is more spread out. It has a larger surface area and more room for it to interact. Whereas this one's more condensed, and it can only really react in this small space here. This is why we have a difference here of a boiling point being 36 degrees Celsius versus the other one being 10 degrees. It's going to take more energy to pull these things apart. Note the linear relationship between the boiling point and the molar mass of the compounds. As the molar mass increases, as the number of carbons and hydrogens increase, the temperature it takes to boil it also increases. So what if it's not just a nonpolar? What if we have something that has a polar charge next to it? The interaction between a polarized or a charged particle and a nonpolar particle is called an induced dipole. So this is something with the charge and something without a charge. The strength varies from 2 to 10 kilojoules. Notice that this other one, the strength is between 0.05 to 40 kilojoules. The starting point is far shorter, far smaller. It depends on the polarizability of the nonpolar particle. So once again, the size. The bigger it is, the more it's able to be polarized. And the charge or the size of the ion. And or if it's a polar molecule and not an ion, the polarity of the polar molecule. As something that has a polar area, for instance this, ends up having a partially negative, like if we have a Cl minus over here. This partially positive, if this gets close enough to it, it's going to be forced to interact. And then it's going to push these other electrons further away. And then that becomes a partially negative area, which is then attracted to another partially positive. And that's if they get really close to each other again. Two ways to induce the dipole moment in a nonpolar particle is to have an ion induce the dipole, and the other one is to have a dipole induce the dipole. So the dipole is a polar bond. And then the ion is either the cation or the anion, which is either a positively charged particle or a negatively charged particle. This interaction explains how nonpolar molecules such as O2 and I2 can eventually dissolve in water. Because remember, water is a polar molecule. We have a partially negative here for the oxygen because it's more electronegative than the hydrogen, and then partially positive near the water, or near the hydrogen of the water. If we have an oxygen molecule, if we force this into the water, eventually it's going to get to the point where this becomes partially negative as it gets attracted to this positive, and the electrons are going to be pulling towards it, making this one partially positive, and then so on and so forth. It gets attracted from one molecule to another. So how about if they don't have a nonpolar molecule to begin with? The dipole-dipole forces bind molecules having permanent dipoles to one another. In other words, these are polar molecules. They're 1 to 5% of the strength of the covalent bond, or 5 to 40 kilojoules per mole, depending on the strength. The strength depends upon the polarizing strength. So in other words, how much of a polar bond is this? How big is it? Things along those lines. Special dipole-dipole interaction is called the hydrogen bonding. Now this is a very specific class of dipole-dipole. The hydrogen originally has to be covalently bonded to either the fluorine, oxygen, or nitrogen atoms. And then that creates such a large dipole moment. For instance, if we have HF here, the fluorine is so electronegative that the electrons automatically drift towards those, making a partially positive and a partially negative end. This creates such a partially positive that it's automatically, let's say we have water here, going to be attracted to that one here, because this will be partially negative and this will be partially positive. This creates a very strong interaction here, so strong it has its own name. H bonding is the strongest when X and Y are nitrogen, oxygen, and fluorine. So let's take a look at that water, because we talked about it in the previous tutorial. H bonding is especially strong in water because the OH bond is very polar, meaning that this hydrogen is going to be partially positive and partially negative because oxygen is electronegative. Just as a small review, fluorine is the most electronegative element. As we get closer to fluorine, the atoms get more electronegative. Oxygen is right next to fluorine on the periodic table, meaning it's really electronegative. Meaning that this bond then, the electrons are going to drift towards the oxygen, creating a very polar bond. There are two lone pairs on the oxygen right here, which then are attracted to the hydrogen of the following one, of the next one over. So you get this positive, negative interaction here that's rather strong. H bonding accounts for many of these of water's unique properties, such as the high boiling point compared to other compounds with similar molecular mass. Liquid's density is greater when it's a solid and not a liquid. That's because as it forms this interaction, it becomes more structured, and it ends up actually spreading out. So there'd be another hydrogen here with this interaction, and another hydrogen here, and so on and so forth. And it becomes very, very structured. And it ends up actually spreading out when that happens to get more and more structured. The high heat capacity is 4.184 joules per gram degree Celsius, which is extremely high because it has to take up a lot of energy for it to change just 1 degree. So it takes a lot of energy to break this interaction here. Let's compare the boiling point to other compounds. These here are all in the same family: oxygen, sulfur, selenium, tellurium. However, oxygen actually has the highest melting or highest boiling point, which is unique because it's the lightest. And that's all because of the hydrogen bonding. The ion dipole moment is once again a permanent dipole, meaning that it's a polar compound. And so if we put an ion in here, for instance, if we take salt and we dissolve it in water, and we look down here, so NaCl breaks apart to be Cl minus and Na plus. The water molecules are going to surround these ions. So here's our Cl minus. Because of this negative charge, the hydrogen is all going to be turning in to be attracted to that chlorine, because hydrogen is the partially positive area. With the sodium, because it's positive, all the oxygens are pointed in because those are all partially negative, and the negative and positive are going to be interacting. The strength of this attraction is affected by the size of the ion and the polarity of the dipole. It's 1/10 the strength of a covalent and intramolecular attraction. And look how much higher the energy is required: 40 to 600 kilojoules per mole. If we look at just the ionic bonds and the ionic attractions, this is even greater, from 400 to 4,000 kilojoules per mole. It's usually associated with the ionic compounds cations and anions, because cations are positive and anions are negative. So it's the positive-negative interaction. Notice that they're whole charges, unlike these, where the charges are partially positive and partially negative. And when they form a crystalline structure, which is a very ordered arrangement. It's the strongest of all the intermolecular forces, and the range is due to the ionic size. This explains why ionic solids tend to have an extremely high melting point for temperatures. For instance, if you put salt on a stove and heat it up, it's not going to turn to a liquid because it's not going to get hot enough. And that's an overview of all the intermolecular forces.